So what we're doing in 9-4 is we're going to be taking a different look at complex numbers. We're going to be taking a more trigonometric approach. So we're going to be looking at the trig form of a complex number. Now we have to remember what a complex number is. It's been a while because we usually deal with complex numbers more in secondary 2. So complex numbers have this form, a plus bi, where a is the real portion, the real part, the real number part, and bi is the imaginary part. That took me a minute. Is that high school? Okay. All right, so imaginary. Okay, sweet. So we have real parts and imaginary parts. So technically, all numbers are complex numbers in reality, because think about it. Right here we have 2 plus 3i. 2 is the real part. There's the imaginary part. Right here, 0 is the real part. There's our imaginary part. Right here, -3 is our real part, and 0i would be the imaginary part. So do you guys see how anything's technically a complex number? All right, now we've got to review how to graph a complex number. So it's just like an XY chart here. This x-axis is the real axis, or the a-axis. And then the y-axis is our imaginary axis, our bi axis. So you actually just graph this like you would an xy point. So do you see how the real part's 2 here in blue? I'd go 2 units on the real axis, and then it's up 3 units, 3i units, so up 1, 2, 3. It would just be that point. So it's just like an xy point. Now the only thing that they'll do differently is they'll give it, like they'll say, starting from the origin, how can I get to that point quickly? The hypotenuse, really, right, everyone? So they'll just draw an arrow pointing to that point. It like gives it, it's like a vector, it gives it direction. Okay, let's graph 4i. So if I said graph 4i, you'd say go over 0, up 1, 2, 3, 4. Does everyone see? Then I just give it direction, pointing from the origin there. All right, let's do -3. So that would be back 1, 2, 3, up 0i. And last one, -1, down 1, 2, 3, 4i. That would be right here. So pretty straightforward. It's just like an XY axis, essentially. Okay. So we're going to talk now how to take it from a plus bi form to a more trigonometric form, an equal true statement, essentially. So it actually works exactly like converting rectangular form to trig form, because the trig form of a complex number, or I mean from rectangular form to polar form is what I meant to say. It works the same way. Because normally, remember last time, this is our x-axis, this was our y-axis, right? And now if I wanted to describe how to get to this AB point, I could describe it instead as theta, comma, go out r units, couldn't I? So that was our polar definition. We're doing that same thing. So if this is, right here is our a-axis, our b-axis, bi-axis, then theta r, this would be a true statement. A will be equal to r cosine theta, which makes sense. Didn't we learn last time that x is equal to r cosine theta? It's the same idea. You guys see? It's just now we're calling it the a-axis. Same thing as x-axis, right? And then y is r sine theta. We learned that. No, my pen's working all day. All right, so then b would be r sine theta. So here is the complex form. Z, they just kind of assign it a variable. Z is equal to this complex number, but it doesn't really matter that much. Z is just a variable. You don't have to use Z, you can use anything. So there's the complex form, a plus bi. Now let's write it in its trig form. So just replace it. Look, what's a equivalent to but in the trig form? So we have r cosine theta instead of a, plus, now b is r sine theta. Do you guys see how I'm just replacing it? So r sine theta I. So that is our answer, but what's going to happen is you're going to see them actually write this in a more factored form. So it doesn't matter if you don't do it in factored form, but you're going to see me write it also in factored form. So in each term, isn't there an r in common? So this is officially how you're going to see them write it. They're going to factor out the r, so divide by r, divide by r. So then left would be cosine of theta plus, and then they'll say I sine of theta. Just for kicks and giggles, they put the I in front. Even though it's usually bi, in a complex number, they put it in front. But it doesn't matter. No, it's the same thing. Does everybody understand that? 2i is the same thing as I times 2. So anyways, so like I sine theta. That's how you're going to see me write it. So here, this is the complex number form, and this is the trig form of that complex number. Okay, so you have that written down, this one right here. Now we'll actually go and use it. Okay, so it says graph the complex number. Now looking at this, it's really easy to graph the complex number. We don't even need to convert. Let's just go with what it says. What's our radius? Based on the formula, look, this is the trig form. So what in the formula, what was our R? 12. So you'd say my radius is out 12 units. And then obviously it tells you right here is theta. So theta must be pi 6. So let's graph this instead of doing a plus bi, the polar form. So where is roughly pi? Here's 0 degrees, everybody. Where's pi 6 roughly? I'm doing a rough sketch here. 30 degrees roughly. So like out right here, roughly 30 degrees, right? So there, now I'm in the correct direction. And then how many radiuses am I going out? So instead of drawing 12 circles, because that gets annoying, I'm just going to do this like line representing a circle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 radiuses. So we're right here. Rough sketch is good enough. And done. So now it says, after you've graphed it, take this, instead of from trig form, we want to put it in its complex number form, which is a plus bi. So you literally just calculate it. 12 is 12, so keep 12 as 12. Now what is the cosine at pi 6? Unit circle should be in front of you today. The cosine at pi 6 is... It's root 3 over 2, right? Then we have plus. Now b is sine of pi 6. So what is 1/2? So we have this so far. You guys see how I've just replaced it with the actual calculation? Now just distribute your 12 in and you're done. So then 12 divided by 2 is 6. 6 root 3. 12 divided by 2 is 6. So 6 root 3 plus 6i. There's your complex number. There's a plus bi form now. Good question. So if you could compare, you could leave it because factor form, standard form equally good. So I don't care if you do factor out the 6, it wouldn't be wrong. I don't care if you don't though. So guys, what if I asked you what's the distance on x? What would you say? What's the distance on a? 6 root 3, isn't it? So this distance from here to here is 6 root 3 in length. Yeah? And then this must be then, if that's true, then this must be 6 in length because that's 6i. Okay, good. Just questioning you. Okay, awesome, doing good. Now this next one's the exact same example, just to re-solidify that knowledge. I would not take notes. You don't need to rewrite the same thing down again. I just want to make sure you're good. So if I said to you, graph this, where would you go? To what? Theta of 150 degrees. What's our radius? 3. So where's 150 degrees? Like right over here? So 150 degrees, and then we're going out 1, 2, 3 radiuses, changing colors, and boom. Okay, good. Now, what's our, instead it says convert it. So what would we do? Just calculate. What is the cosine of 150? Root 3 over 2 or negative? Okay, and then we have plus I, then times by 1/2. So we take 3, distribute in. So wouldn't we get negative 3 root 3 over 2? Right here. Plus 3 over 2i. And that is the a plus bi form. So pretty easy stuff. Okay, great. Okay, let's write this one down. Let's go the other way. So this says, write this a plus bi, this complex number, instead in its trig form. So we learned a second ago that you can take an a plus bi and you can convert it, and it's going to become r parentheses cosine theta plus I sine theta. We just gave you that formula a second ago, right? So what you're always going to do when you're having to convert from complex to trig, you're going to want to draw a picture so you can get it in the correct quadrant. So we're going to go, and we know this is our a, this is our bi axis. So we're going negative 2 units. A rough picture is good enough. Negative 2 units, and then up 2i units. So I would draw a right triangle here. So this was negative 2, this is up 2 units. Does everyone see? So now here's what we need to know for this formula. We need to know our radius and we need to know what theta is. So radius is equal to, well, how would we find the radius? Pythagorean theorem, isn't this the radius of our circle, everybody? So you'd say, okay, well, let's do it. So negative 2 squared plus 2 squared equals radius squared. 8 equals radius squared. Square root of 8 equals radius. So then doesn't that equal 2 root 2? So our radius is 2 root 2. And then our theta, you'd say, well, okay, to describe how to get to this same point, aren't I starting at 0 and saying go this many degrees? That's the appropriate way, but really, can't we only find this angle for right now? So how do you know it's 45? You're right. Right.
Yeah, because it's 2 and 8, so it's 2 and 2, which means it has to be 45.
So, okay, so we can set up any trig ratio, right? Sine, cosine, or tangent. I'm going to choose the whole numbers always, because to me it's better than having to do radicals. So it's opposite adjacent. So isn't my true statement tangent of theta is equal to 2 over negative 2? So we're looking for when does tangent of theta equal negative 1? Does everyone see what he's saying? Which, go to the correct quadrant. It must be in quadrant 2 if this is our point. Therefore, doesn't tangent equal negative 1 from here up to here 45 degrees? We can't use 45 degrees though. We have to use from 0 to here. So what's the degree measure? Good, 135. That's considered a reference angle. Okay, so let's write it. I'll plug it in. We have 2 root 2 is our radius times by the cosine of 135 plus I sine of 135. And now it's written in its trig form. Done. So we just had to hurry, draw a picture, find r, find theta. Now the next one you're going to see, so on this one, our theta was an angle on our unit circle. Let me show you how to write an answer, how we're going to want you to write the answer if the angle happens to not be on the unit circle. So let's do one more like that. So this is another one I'd probably write down for myself. So we have z is equal to 3 plus 5i. That's a plus bi form. And we want to take it to r cosine theta plus I sine theta. So then to do that, we need to know what our r is, and we need to know what our theta is. So you'd say, well, I'm going to draw a picture. Once again, I highly recommend. So out 3 units, up 5 units. So I would do Pythagorean theorem, 3 squared plus 5 squared equals radius squared. The square root of 34 equals our radius. Now that doesn't break down, so we'll leave it as a square root of 34, my friends. Does that make sense? So square root of 34, we're almost there. Now you have to figure out what theta is. So you can set up any true statement to do this. So my true statement, I always choose to go with the whole number, so opposite and adjacent. I'm dealing with tangent again. So my true statement is tangent of theta is equal to 5/3. Now that is not a unit circle amount, correct? So isn't this the one appropriate time it is to take an inverse? So we take the tangent inverse of both sides. So now look at my true statement. Theta is equal to tan inverse of 5/3. Now question for you. Do you want to put theta as radians or degrees? Well, it does not matter. Aren't they the same thing? So when you check the back of the book, what if you chose to put it in degrees? And they have radians. Does that mean your answer is different? No. You just happen to choose something different than them, but it's the same thing. Does that make sense? Okay, now if you type into your calculator, and let's say you have it in degree mode, let's say you want to put a degree measure as theta. Type it in, and I'm going to make a point here. Tell me what you get. And then you just gave me a rounded answer, true? We have no choice but to give a rounded answer because it's not on the unit circle, so we can't give an exact answer. So instead of giving a rounded answer, so that this is a little bit off, instead they're going to say, well then, theta is tangent inverse of 5/3. They don't actually calculate it, they leave it, so that it's an exact answer. Does that make sense, everybody? So then plug in that. So you'd say, okay, r is square root of 34, so we have square root of 34 times by, then we have the cosine of theta. Now once again, we're calling theta tan inverse of 5/3. Then we have plus I sine of theta, which theta is tan inverse of 5/3. Do I have a weird extra parenthesis in there? Look at it. Go away, go away. Oh, cancel, cancel, cancel. Oh, right here. I need to kind of like, because this is the cosine of tangent inverse. And then now my plus sign is all jibbled in there. Does that make sense, everybody? Okay. So if it's not on the unit circle, just leave it written as the inverse. Okay, good, 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 good. Doing really good here, flying through this. So, looking at this next piece, I think we get that picture here. Come on, computer, let's get the show on the road. Okay, so now we're going to talk about multiplying and dividing the trig form of a complex number. Now, I need you to understand, if I said to you, take a plus bi times it to c plus di, those are two different complex numbers, correct? Wouldn't we just do that times that, plus that times that, plus that times that, plus that times that? Yeah, and then we'd have to change all I squareds to -1 and then combine like terms. So now we're taking, and instead of having the complex number, we have the trig form of the complex number times to the trig form of the complex number. Now, we could do this by hand the long way. If you look at this, wouldn't it make sense that radius 1 times radius 2 could be pulled out in front? But then wouldn't we have to double distribute? Combine like terms, change I squared to -1, yada, yada, yada. That would take forever, correct? So I'm telling you, we could do that, but it will always end up being this. It'll always simplify to be this. So this is the formula we're going to use instead of having to do it out the long way every time. So writing that down. Now, if you want to see where this comes from, we could show you, I could show you one-on-one, and we can also look in our book, which we just handed in. So we would have to pull that back out, and I could show you, but that's fine. But like I said, we could actually do this by distributing. So this is actually what it's going to happen here. We're going to take radius 1 times radius 2, put it in front, which makes sense. Then we're going to have cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. So they just add, like, look right here, this first angle will be your theta 1, this second angle will be your theta 2. So they just took the cosine, added the angles, plus I sine, add the angles. Yes? Yeah. So now let's look at a division one. If we have R1 divided by R2, just a reminder, if I had a complex, this is the trig form of a complex number. Let's say I had a plus bi, the complex number, divided by c plus di. Does anyone remember the problem here? Well, we have an imaginary on bottom. So how did we get rid of that? Can anyone remember? We have to multiply by c minus di. C minus di. And then do you guys see how we would have a nightmare of a problem? Kind of? So the trig form of a complex number, we'd be multiplying by cosine of theta 2 plus I sine of theta 2. And then we would be having to multiply by the conjugate. So it would get messy. We could do that, and then it will always be this. So you can just write down the formula, and then we'll just use that instead of actually doing it by hand the long way. So you just take R1 divided by R2, which makes sense. And then we have cosine plus I sine of theta 1 divided by cosine theta 2, sine theta 2. And so now notice what's the difference. Instead of add inside, we subtract, which makes sense. When you multiply, you add. When you divide, then you subtract. Now the one thing that is the same is the plus sign in between. That stays the same. So it's really, you're going to see how easy this makes our life. Like, so easy. If we didn't know this formula, it would take forever. So here we do. First example of this, we'll only do one of each. It's pretty quick. So you'd say, oh, these are two trig forms of complex numbers being multiplied. Here's our first trig form of a complex number, second. So we would just reorder it. That's 2 times 3, is it not? 2 times 3, and then we are told that we can do cosine of pi thirds plus 11 pi 6. Right? And then plus I sine of the same thing, of pi thirds plus 11 pi 6. So now let's actually do that. We have to actually calculate that. So now what you're going to do is get a common denominator So let's times by 2, times by 2. Good, so we have a 6 parentheses. We have the cosine of 13 pi 6 plus I sine of 13 pi 6. So now we're going to go through. Now, if they want the trig form as an answer, aren't we done? But I think they want us to write it out in a plus bi form. So all we do now is actually calculate that. So what is 13, the cosine at 13 pi 6? Look at your unit circle and locate 13 pi 6. Now think about it. Isn't 12 pi 6 2 pi? So don't you just go up one more pi 6 amount? Yep, it's 30 degrees. So our coterminal angle, right? Perfect. So this is the same thing as 30 degrees, everybody. Same calculations, I guess I should say. So the cosine at 30 degrees was root 3 over 2, is it not? So then we have root 3 over 2 plus I, and then the sine at 30 degrees is 1/2. So now you take 6, distribute, distribute. So our final answer would be 3 root 3 plus 3i. Okay, good stuff. Okay, let's do a division one. Now remember, the only difference is when you divide, you subtract your thetas. So in this one, don't unaccidentally subtract 24 minus 6. No, no, no. That's a number being divided by a number. That's not what we're talking about. 24 divided by 6 is 4, right? So we have 4, and then now we have cosine of, you'll take the top minus the bottom. 150 minus 30. 120, right? Plus I sine of 120. When you divide, you subtract. That's why I subtracted. And now all we have to do is calculate. So you would go to 120. The cosine at 120 is negative 1/2 plus I, and then the sine at 120 is root 3 over 2. So distribute. So we get negative 2 plus 2i root 3. And we're done. Yeah, so factor form and standard form are equal, right? So it wouldn't be wrong if you did, but it wouldn't be necessary if you did not factor out a 2. Valid question. Okay. All right, we're almost done. Last thing we have to learn. It's quick-ish. Okay, so here's the thing, guys. If I give you this problem, if I said take 2 plus 3i raised to the 10th power, that's going to take us a dang long time. We would go, the only way we know how to do it so far is to make a Pascal's triangle clear up to degree 10, right? Put in all those coefficients, then take your front thing, 10, 9, 8, 7, 6, 5, 4, 3, 2, blah, 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 take the 3i, 0, blah, 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 catch your, you know what I mean? Okay, it's going to take a long time. So we're learning a quicker way right now. So here's the thing. If you take a complex number and instead write it in its trig form, which we know is r cosine theta plus I sine theta, and then raise it to the degree, you can use what's called de Moivre's theorem. So de Moivre is a mathematician that figured out that this is always the calculation of this, raised to the 10th. So it's kind of cool because if we have this trig form of a complex number raised to the n, if you want a proof of why this de Moivre's theorem works, you need to look up online, type in why does de Moivre's, or proof of de Moivre's theorem, watch it because I'm not going to go over it. But what we do is take degree n and we take r raised to the n. Do you guys see how that's in our formula? Which makes sense. Now I have a lot of people say, but that's breaking the next part's breaking the forbidden rule, Miss C. So raise that to the n, raise that to the n would be breaking the forbidden rule. That's a plus sign. You can't do that. But that's not what de Moivre's theorem did. The n is multiplied to the theta inside. Now once again, if you're like, well, why? I'm not showing you why. You're going to look it up on the internet of why this works if you so desire. Does that make sense? Because I'm not going over it. Okay. So look how nice that's going to make the calculations. Because then after that, boom, you just go. It's way quicker than having to do it this way. So write that down. R cosine theta plus I sine theta raised to the n will be r to the n, and then cosine of n times theta plus I sine of n times theta. You just take n, multiply it in. Here we go. Example number 1. So this is already in its trig form, and it says take this and raise it to the 3rd power. Now the long way would be to rewrite it out 3 times, double distribute, combine like terms. That would take a long time. Agreed? So we're going to do it with the Morse theorem. So what can we do? We can take 3, put it here, so that's 2 to the 3rd. Then in our parentheses, you can take 3, multiply it to our theta, take 3, multiply it to our theta. So then we have the cosine of, instead, 9 pi fourths. And then we have plus I sine of 9 pi fourths. And now we can just calculate. So 2 to the 3rd is 8, parentheses. The cosine at 9 pi fourths, you'd go to 9 pi fourths on your unit circle. 9 pi, here, right here, where is 9 pi fourths? If you don't know, is it pi fourths? Right here? Why? But because you're saying, right, okay, sorry, say that like this then, just for the video. You're saying this is 8 pi fourths, which is 2 pi, that's why going 1 more pi fourths would put us, okay. Cool, so the cosine at 9 pi fourths is root 2. Oh, we should know that one without even looking. Any pi fourths, right, is always root 2, root 2, root 2, root 2, and then it just depends on the quadrant if there's any negatives. So then we have plus I root 2 over 2. Almost done. Take your 8, distribute, distribute. So aren't we going to get 4 root 2 plus 4I root 2, and we're done. A plus BI form. Does that make sense? Let's go. Yeah, let's go. Are you guys understanding? Okay, let's now look at this bad boy. Okay, so we have 1/2 minus 3 root 2 over I raised to the 5th. Now, if we were so desirous, we could make a Pascal's triangle, true? Right, our coefficients, that would take forever though, correct? So wouldn't it be better to take this A plus BI, convert it to its trig form, and then we can use de Morse theorem instead? So let's convert it. Now remember, how do we convert? Well, we drew a picture, didn't we? So let's do that. So that would be right 1/2 down root 3 over 2, like this. 1/2 negative root 3 over 2. Now look, here's your x, here's your y point to get here. Isn't that an xy point on the unit circle? Therefore, what's the radius without even doing any math? We could do Pythagorean theorem, but we could also just think about it. Since this is the unit circle, what would my radius be? 1, right? We could do the math, you'd get 1. Well, just remember that the radius on the unit circle is 1. Yes. Well, yeah, like we could go through and do 1/2 squared plus negative root 3 squared equals radius squared, and do it, and you would get 1. Everybody good? Okay. So now from here, we would say we need our r, we need our theta. So what's our r? We just found it to be. What's our theta? Well, we're in this quadrant. So you just said it's what? 300 degrees, because what's the xy point in this quadrant with 1/2 negative root 3 over 2? At 300 degrees. Is anybody confused why we're saying 300 degrees? All right, so let's go rewrite this. Sorry, I'm almost done, Robert. So we have r, which is 1, and then we have our cosine of 300 degrees plus I sine of 300 degrees. And then now we're raising that to the 5th. And now de Morse theorem allows us to quickly do this. We'll take 5, 1 to the 5th, true? Take 5, multiply it in, multiply it in. So we have 1 times the cosine of 1500 degrees plus I sine of 1500. Now let's get down. That's way big, isn't it? So shouldn't we find coterminal angle, start subtracting to a 60 like a crazy person until you get back to the unit circle? Or just to get back to a decent angle? What? So we could write 60 degrees because that'll have the same sine and cosine calculations. True? Okay, so what is the cosine at 60 degrees? So we have 1/2 plus. Okay, so root 3 over 2 I. Okay, good. And then we times by 1, right? Yeah. So we just calculate at this point? Yes. Now, didn't our answer come out to be A plus BI? That's what we want, right? If you would have done this the long way, you would have got the same answer. Wasn't that much quicker?
Will it, like,
I don't know sometimes.
so if,
Yeah, if it was to even bigger. What are you saying, Jackson?
so if like the radius and like, so if the radius is 1 and if it like corresponds to the points on the circle, will it always come out to be what it's starting to be?
No, but that was a valid question.
Because it didn't start out the way it was.
Oh, right,
True.
It's a different quadrant.
True. Okay, great job. That's the end of, wait, let me make sure. Yeah, that is the end of the lesson. So go to the paper and do those problems. Ready, set, go.